Since I'm local, I don't have to introduce myself, the speaker. Anyway, thanks for coming to the talk series. My name is Joy. I'm a research faculty here, one of the first research faculty hired on this campus 3 years ago. When I first was interviewed here, there was not any major activities in the daytime. I was so happy to see that the campus grows so fast, and now we actually run out of space. The reason I was hired here was because of the setup of mobility center, and I redirect part of my research to the mobility research, and that will be part of my talk. So there are two lines of my research since I joined the faculty here. The first part is the natural language processing application for mobile applications, for mobile platforms, including a mobile speech-to-speech translation, one of the products that has been commercialized through CMU spin-off companies called Gibigo, G-I-B-B-I-G-O. It's one of the first and still one of the only mobile speech translation system that runs solely on the mobile device. Part of my research has also been involved with the mobile sign translation. That is like when you go to China, you don't understand the Chinese, and if you see the road sign there, you have no idea what it means. You take out your mobile phone, take a snapshot, take a picture, and the mobile sign translation will automatically recognize the sign and translate from Chinese to English so that you know this is not for tourists or danger ahead. The other project, I'm working with some other folks here, Stephen and also Martinez, on strategic reading. The basic idea is that nowadays you are overloaded with information, such as if you are a pilot, you have to carry 1,000 pages of a flying manual every time when you fly. That's just not possible. Now, United Airlines and some other airlines are giving their pilots the iPad so that you don't have to carry this 50 pounds of manuals in paper with you, but you have to carry all the information with you. Now, the idea is, what if you have some emergency situation, 30,000 miles in the sky? Now you have to go through this 1,000, 2,000 page of manual trying to find the solution. That's just not possible, even it's on iPad, because it's still in a linear order. So what we are intended to do in this project is to have a situational aware, context aware system that can generate a book for dummy in a short period of time, so that you just tell the system, how do I do crash landing? And we just pop out a short checklist for you to do. The other project is context aware language processing. We just published a paper at MT Summit. Now the idea is to extend the speech translation system we had experienced with Gibigo, where you have the mobile speech-to-speech translation system. But in the Gibigo system and most of the current speech translation system, the system is not aware of the context. So the system does not know whether you are in an airport or at a bar or you are trying to get a hotel reservation. Now we know that natural language are very ambiguous. Right? When we have a communication, for example, I can just say the word black bean. If this sentence happens at a grocery store, and if I'm talking to a grocery store clerk, then the answer will be very simple, I agree. Because the clerk knows that my intention is trying to find the black bean. But if I come back home from grocery store, my wife asks me these two words, black bean, my answer would be very different. Oh, sorry, honey, I forgot to buy them. So the same sentence have very different meaning and will have very different reaction because the context is very different. Now, in this research, we're trying to bring the context information into the big picture of statistical machine translation, or in general, speech translation, such that the system will be more aware of what we're doing, to be more intelligent, to narrow down ambiguities in natural language. So this line of work is mainly sponsored by DARPA, Department of Defense Advanced Research Agency, something. So we have been involved with the TransTech project in the past 5 years. That is the military trying to give us research money to develop a speech translation system for the soldiers used in Iraq and Afghanistan so that they can communicate with the local. And we have been involved by the Transformative App project, where military is trying to develop a concept called the military app store, just like they see the success story of the Apple iTunes store, so that the grassroots software developer can develop intelligent apps on the Android phones for the soldiers to use. Then they can just pay the developers instead of go through the DARPA money. And we have just been awarded the BOLD project, BOLD program. This is the second phase of the Gale and the TransTech project to develop broad operational language translation technology. The next 5 years, we will be developing the new generation of the speech translation technology. Since I joined the faculty here, I have been doing something new using my expertise in statistical natural language processing for some non-language problems. In particular, user behavior modeling, which is the focus of this talk. We have been using algorithms developed for statistical natural language processing for mobile computing, such as for activity recognition and human behavior grammar induction. We have several papers there. Anomaly detection, geotrace modeling, and this line of work is supported by the Army Research Office, Scilab, Cisco Research, Google, Motorola, Yahoo, Nokia Research, and we have just been awarded by the DARPA TCTO program called Healing the Heroes. So the idea is, with all these mobile phones the veterans carried with them every day, how can we use that to identify their social behavior? Because the statistics has shown that on average, about 18 soldiers, veterans, killed themselves after they returned from the battlefield because of PTSD and lack of social support. Now, DARPA, one of the psychologist, who is now the DARPA program manager, is trying to use the new technology to help the veterans to solve their social problem, at least understand them, their social needs, so that we can better help them. Now, I don't have to tell you that a mobile phone is everywhere. If you get off the airport and you're looking at all the passengers waiting for the taxi or the ground transportation, everybody's doing this. Checking email, texting, or checking the information. According to the studies by Cisco, it is projected that by 2013, on average, 51%, more than half of the phones in the US market will be smartphones. Android, iOS, Blackberries. And this will be about the same around the world. So I think that's the future. It's obvious to everybody now. And we have just done a study on low-income minority women in the Central Valley area. One of my collaborators was trying to study how the smartphones reflect the usage among the low-income women, minority women. At first, I was very suspicious about this study. You know, if the people cannot afford the rent, if they need the social security check every day, why do they need an iPhone, which is $500? But surprisingly, there's a high percentage of the population in this group actually has a smartphone, more than 30 to 40%. Now, during the interview, I think it is very obvious when we looked at the interview why they need a smartphone. Because they cannot afford the internet at home, they cannot afford the PC at home, they need some way to communicate. Nowadays, you have to use email, you have to use text messaging to communicate with your peer. So they choose iPhone or Android phones. And this also is a good symbol for them to show that their social status. So one of the interviewees said in their answer, when she went to the when their friends reunion, at first everybody was looking down at her because she's low income, she's a single mother. But when she bought an iPhone, she took out the iPhone. Everybody was like, "Wow, she's a different person because she's so techy now. She has a very stylish iPhone and she can do texting and play Angry Birds on her iPhone." That really changed her image among her friends. So that's a very interesting trend, and we are following up on this study with a sponsor from Google. Google just awarded us 20 Android phones to continue studying this line. So why do we do mobile sensing? We believe smartphones is a very good platform for us to sense the society, sense the people. In the old days, people put sensors on the human body to sense different activities of the user. It's very cumbersome. Right? You cannot imagine we put some cool embedded sensors, such as accelerometer to trace your motion, gyroscope, receiver to record your outdoor location, Wi-Fi, Bluetooth, NFS for some indoor locationing stuff. And you got a microphone, camera, you got a temperature, light sensor. You can consider the clock and the calendar as kind of soft sensor so that you know what time is it, what is the user's agenda. Smartphones are constantly connected with the internet, so we don't have to solve the problem as the ad hoc network people has to build up the network on the field. When your phone is with you, usually your phone is connected through 3G or Wi-Fi network so that we can upload all the sensor data constantly to the cloud. And through the phone, because it's connected, you can view the information computed on the server side in the real time. And most importantly, users carry the phone almost at all time, except for a certain group of users who prefer to put their phones in the purse. We don't have a good solution to that. One of the anecdote with that is that when we did the activity detection for a certain group of users, more than 25% of the time, the phone says they're idle because their phone is in their purse, and the purse is usually somewhere on the table. But in general, user carries the phone all the time, so my phone knows where I am, what I'm doing now, and my future activities. In a way, my phone knows better about me than my wife. My wife doesn't know I'm giving a talk now, but my phone did. Yes?
Are you going to talk about the relative utility of sensors in the phone versus outboard sensors?
Probably not. Just give a brief overview. So if we can really do a good mobile sensing, there are a lot of interesting applications that can derive from this line of research, such as activity logger. So one of the applications we have been developing is called a mobile life logger. My phone records everything about my life. And this would be very useful, such as activity summarization and time management. If you run a small business, you know what I meant. Every year around April, you have to dig out your old receipt to find out what you did last year so that some part of expense can be charged to your small business. Some of the charge will belong to your personal income. And it's a nightmare if you travel a lot and if you have lots of activities. Now, if you have this kind of application, it can generate a summarization so that you know what happened in your past. If we can really derive the behavior model, then we can develop a personalized behavior-aware application, such as personalized TV, or we can forecast the user's behavior model, such as projecting which ads can be shown on the mobile device, such that it will be most effective for the ad deployer. We can have a personal behavior monitoring, such as in senior care, well-being, and health monitor. So if I carry my phone every day, my phone can tell me, Joy, you have been spending too much time in front of the computer, better get out and enjoy the outdoor so that it will be better for your health. And for security and anomaly detection, I will give one example towards the end of the talk. If my phone monitors my behavior, it knows what is normal for me. For example, my geo-trace, the way I hold my phone. Now, if my phone is stolen, it can send out the alarm and flag the behavior such that it can do something about these anomalies. In the extreme case, the phone can go self-destruction mode if I got really sensitive data on my phone. Now, if we expand this work towards the society level, we can really do social behavior understanding, such as deriving the enhanced social graph out of the mobile sensing data. Currently, when we talk about social behavior, talk about a social graph, most of the activities are derived from online behavior, right? Your Facebook activity, your Twitter activity. But in reality, what matters most about your happiness is how much time you spend with your friends in the physical social network, not how much time you chat with your friends on Facebook. There has just been a study called What Matters to Your Happiness. And one of the key factors is that you need to spend at least 6 to 8 hours in the physical world doing social connection. That will make you happy, not on Facebook. So with this, we can use the mobile phone, mobile sensing to understand your social behavior in the physical world so that we can better understand whether you're happy or not or how to improve your well-being. So this is related with this Doppler Heating Hero project. Where we will study the veterans' social behavior such that we can improve their social behavior, improve their well-beings after they're coming back from the battlefield. So all that said, it's fantastic if we can do it, but it's not so easy. Right? There are many challenges in in the mobile sensing. The first challenge is how do we understand all the meanings from these heterogeneous sensors? A phone comes with different sensors. They have different sampling rate, they have different semantic meaning, they have different representation. How do we make sense of them? The second challenge is, can we recognize high-level activity instead of just the low-level activities? Right? If you go to the literature about activity recognition through mobile sensing, a lot of them are focusing on low-level activities, such as training a classifier to recognize if you're walking or standing or sitting. But when we looked at the data, people return to us, what they really care about are high-level activities. I want to know how much time did I spend shopping at Costco last month. as a high-level activity. It is composed by several steps of low-level activities. But currently, the state-of-the-art activity recognition are not doing that. Third challenge is the ad hoc approach versus more generalized framework. Again, a lot of people are doing activity recognition. They're just training an ad hoc classifier, but by taking some sensor input and trying to recognize that after the model is trained. But what we are looking at is to create a more generalized framework such that it's more flexible and we can separate data representation versus algorithm so that we can try different things. The fourth challenge is that we have very few labeled data in this research. Annotated sensor data and activity data is very time consuming and very tedious. But we need those annotated data so that we can understand the meaning of the activity. And sometimes if we want to train the supervised activity recognition, we need those labeled data. But again, you can't just hire some graduate students sitting in front of the computer and annotate what people are doing for that 10 seconds or for that half an hour. It's just impossible. It's a very cognitively highly overloaded task. The other challenge is the accessibility of mobile phones. So the sensors available and the positions where you carry the phone actually have a big impact of what kind of activities they can sense. So for example, the current technology will not give us the power to distinguish whether the user is driving the car or sitting on the passenger seat of the car, because everything sounds the same. The speed, the vibration, the noise environment. So that's a challenge. If we really want to separate these two cases, we probably need more sensors. I haven't figured out what's the best sensor we can put into the phone to distinguish whether you're driving or you're sitting in the passenger seat. Privacy issue, of course, we're collecting a lot of information from the user. How do we protect the privacy of the user? Power consumption, that's a typo here. If we blindly turn on all these sensors on the phone, it will drain up the battery in about 4 hours. And if your phone will die in 4 hours, nobody's going to use it, especially if you are traveling outside. That's just causing a lot of troubles. So that's the challenge, and I think we have some solution to solve some of the problems to some degree. Now, the core idea of our research in our group is called behavior text representation. It's a simple idea. It is based on the observation that human behavior share a lot of characteristics that is common with natural language. As natural language, the meaning of the human activities are composed from the meaning of the building blocks of the small components. So what do you call this? Why do you call this activity shopping at Costco? It is composed by several small components where you get off the car, you drive to the Costco, you get off the car, you get a shopping cart, you show your car, you show your membership card to the shop clerk, you enter the Costco, you shop around, you take the stuff to your cart, you check out, you unload everything to your car, you drive away. So that's the whole procedure. And each step has some semantic meaning. And it is because of the composition of all these building blocks that makes you derive the meaning of this high-level activity called shopping at Costco. Okay. It's very similar to natural language. And similar to natural language, the human behavior is expressed as a linear order. For natural language, when you want to express a meaning, what you have in mind is actually a structure. There's a subject, there is a verb, there is object, there's a semantic relationship between each other. But because of the way we speak, we have to speak one word after another. You have to express yourself in a linear order. So all the natural language processing is trying to do the other way, trying to unveil the underlying structure from the expressed surface form, the linear order. So we think that's the same for the human behavior. What my phone recorded out of all the sensors is a linear sequence of all the sensor information. Now we want to find out what is the underlying structure or what is the underlying meaning of my activity out of this linear order. So that shared a lot of common characteristics as the human language. Yes?
That's a very exciting idea. The thing that's interesting is unlike a stream of audio, with this sensor fusion, we have some things that are parallel and some things that are linearizable. And I'm just wondering, do you have some change in the syntactic structure of language that's going to have to do with the parallel nature of many of these sensors?
Parallel, you mean different sensors, right?
No, I mean simultaneous.
Right, simultaneous sensors. Right. In a way, it's similar to natural language.
No, natural language, you have one word after the other.
Right. But
This is very
for
different.
each different word, it has different morphology. They have
No,
different
but
factors.
many sensors are going to talk about the same word.
Yes.
So there's parallel.
It is parallel, but if you think about each word in English, you take out the factors. You got the word stem, you got the prefix, you got the suffixes, right? If you think about them as different factors in your word, then they are in parallel. But what you observed is a combination of different factors. So in natural language, we have, like, for example, factor language model is doing the similar as what you said. Yes.
Well, there is a danger that you just assume this, because your brain is parallel and your mouth is serial. And he's pointing exactly at the issue. Everybody rationalizes serially and thinks parallel.
Mm-hmm.
And there's a massive misunderstanding applying logical thought, which is serial, to all thinking, and that's why computers can't think. We have been trying to make them think as we speak instead of as we think. There is an enormous amount of power in parallel. And it's so funny to watch parallel computers try to serial think, because we're still not good at logic that's parallel.
Yes. But that's a very good point. I think that relies.
I'd like to talk about this more,
Yeah.
because if you take a word and it has a suffix and a prefix,
Right.
the multiple sensors are much noisier than that. They are actually separate from each other. They're not part of a coherent, word. Somewhat different.
It's not exactly the same. I agree with you. Yes. I think.
I like your.
Yeah, but I think the reason why we take this analogy is that we can reuse a lot of algorithms.
Right, you can't, right? Not necessarily. You're going to have false.
There's some, yes. There's some mismatch. Yes. Ben.
The previous slide, you mentioned the difference between knowing. Sorry, I should be pushing this.
I think it's
Oh, no,
all on.
already
No, no,
on.
Yeah.
Okay, you mentioned the difference between determining whether it's a driver or passenger. I know that problem's hard, but if you or anyone here can get a solution to that, you can probably get a bunch of funding from the FCC, because they are trying to decide whether they should recommend cell phones to be just blanket illegal in the car. And the crux of the whole problem is knowing they don't want to outlaw it for the passenger, but they do want to outlaw it for the driver.
Yes.
So the crux of they're looking for technical solutions, an app or something. And the whole problem that just boils down to, how do you know if it's the driver or passenger?
Exactly.
And that's what all the solutions boil down to. And if you do that, you can solve a problem that a lot of little startup companies are getting funding from FCC to solve. So
Yes.
there's funding for that.
I agree. I mean, that's why, you see I got
It's a
lots
hard
of
problem.
collaboration from the industry, because it's a very exciting area, but
Yeah.
that problem is a hard problem.
But that's one that people are really looking for.
We thought about one solution. If the phone is mounted on your arm, that's probably going to have some impact, because you're going to use that to steer your wheel, but most of the cases, the phone is in your pocket. Yes.
I think there are other solutions. You can use NFC and sort of scan a tag as you sit down. You could use short-range RFID.
It's possible, yeah. That requires some infrastructure. Yeah. Okay. So here's a table that takes draws some analogy between natural language and the human activity. So you see there's a building structure by composing the lower level activities together in a sequence to creating high level activities or high level meanings, similar in language and in human activities. Yes.
Would there be an advantage to, as you go up, to thinking about word, phrase, sentence, and then scene and story? Because
Story is a good term. Yes.
It seems like it becomes more meaningful.
Yes.
As you go up that way.
That's a good point. Yes. So if we take that analogy, my phone is like a pen, and if I carry the phone with me all the time, my phone is writing a book. It's called the Book of Joy, recording everything about my life. Now, if I have this Book of Joy, then I can apply all the statistical natural language processing to process everything about my life. Find out what I did last week, find out how many time I spent with my kid, how much time did I spend shopping. I brought up the issue at the talk, saying that now with this technology, I can show my wife how much time I spend actually taking care of my daughter and how much time you spend on shopping. And I got advice from a married man, don't go that way. You will lose our discussion anyway. Okay, that's just side talk. Now, so we have been developing all these cool algorithms in statistical natural language over the past several decades: information retrieval, machine translation, text categorization, summarization, prediction. Now, with all this analogy, I can just apply these algorithms on the data and deriving the meaningful applications pretty fast. So here's what we do. The first step, what we do is by converting all this multi-sensor data into a behavior text representation. It's just like symbolic representation. So for example, you got the Wi-Fi here, you got the compass, you got the time, this is Wi-Fi, this is tower, this is the 3-axis accelerometer, this is the GPS coordinates. For different sensor, you want to extract the meaningful representation. So you have to really looking at the characteristic of each sensor. For example, for the accelerometer data, we use quantization. For the GPS coordinates, we can do clustering. So once you're converting the real number sensor readings into a symbolic representation, even though you lose some precision of your sensor, but this makes the follow-up processing much more easier. For example, the 3-axis accelerometer data, which is becoming a sequence of labels. And to me, I don't really care about whether fi corresponds to this vector or that vector. I just need to know if I is a value in my sensor reading. And if there are two sensor readings the same called fi, they will be the same. So with that, I can apply all the magics to process them. So we have been, yes?
There's an analogy here to what the FAA did for flight tracking on radar returns. And there are a significant amount of work in smoothing and look-ahead algorithms about data points to discard. Because if in the middle of my Costco trip I go to the bathroom, it doesn't add to the shopping semantics.
Yes, there is a danger, yes. For example, when we did the GPS partition, GPS coordinates partition, we just basically do a density-based partition. So there is a danger, for example, data points could be at the boundary, could be very different in a way, yes.
But there's a synthesis activity you're alluding to but not specifying. Strikes me a difference between natural language. If the natural language came first, and here the higher order structure comes last. And you're synthesizing from low-level data and actually inventing higher-level meaning.
So what do you mean inventing a higher level meaning?
Synthesis is the best word I know.
Right.
There's a whole bunch of very, very minuscule locations, communications bits, and does it mean I'm having an argument?
I see. I see.
It's a pattern origination. You can do it by fit, but you're trying to originate a concept to go with the measure.
You have a presupposed hypothesis of what you would do.
Yeah.
That's the flaw.
That's right.
It doesn't see it, it recognizes.
So what we have been working on is creating a social sensing platform called CMU MobiSens. It contains 3 parts. One is the mobile app. This is now an Android app you can download free on your Android phones called CMU MobiSens. It basically collects all the sensor information, aggregate the data, and communicate with the MobiSens backend. It's a server running on our campus. It can get all the sensor data, push back the model so that we can constantly update the model on the different users' app. Of course, push the model, update the data, and the MobiSens backend aggregate the data, store the data, do some pre-processing, and based on that, we can develop the second-tier service. For example, the life log service, activity summarization. You can have the behavior modeling, all based on the second-tier services that gets the data from the MobiSens backend. It's a very complicated system, but it's running for multiple months already. So for example, one of the second tier services called the Life Logger. We actually have this running. This is once you uploaded all the raw sensor data after the pre-processing, you can view your life logger. For example, this is the students going to Lake Tahoe and had a ski trip there and got the mobile phone mounted on their helmet so they can take pictures every 10 seconds or something, basically show what they were doing there, overlaying the GPS coordinates on the map. You can play the sound that is associated with the life log. You can annotate the life log for that activity. And if you highlight a segment of the activity, you can use information retrieval to find similar activities in the past. For example, if you highlight the segment of activity that you fell down on the slope, you can find out all the similar activities so that you know by the end of the day you have been falling like 20 times on the slope. But yesterday you fell 40 times, so you're making progress. So that's the second tier applications. So we're not claiming we're the first one who developed the social sensing platforms. There have been multiple efforts among the community trying to use the mobile phones to sense the people's behavior. For example, the simple context effort by Nokia Research Center is basically running on the Symbian platform, collecting all the sensor readings and upload it to their data server. And whoever wants to do that, they will just do the data mining on the data. The fun stuff by the MIT Media Lab, which is also part of our DARPA project, it's also a data collection effort. It's an open source Android app that collects all the data. So far, the data are stored locally, and if you are a developer, you have to work with the users to get their data to do some analysis. The SenseMe stuff by this is Dartmouth College. It's a two-tier built-in classifier. They can recognize a limited set of activities that is predefined. It has multiple data modality. It's doing the presence sharing among the friends. So in a way, quite similar to our stuff. But our stuff, MobiSens app, is very different from them, and we think we are leading the game because we are doing on-device automatic activity segmentation and recognition. And I will show later in my talk that this has significantly changed users' participation in our study. So like all other social sensing platforms, we record all the mobile sensor information. As I said, our mobile device will do the on-device activity segmentation and recognition. And on the latest version, you can share your current activity with your friends, so that my wife, knowing that I'm giving a talk here, so that she will do something different. So this is the screenshot of where users annotate and annotate their activities. It's automatically segmented so that you know at what time there is some different activity. The user can provide annotations to a activity that he or she is interested in. And you can also show your trajectory, show your path over. Yes.
I can label activity. I can say I'm taking out the garbage.
You can do whatever you want. You can create a code name. For example, somebody's meeting their secret lover. In order not to be discovered, you can say paying tax. So it's just you creating a name. It doesn't have to be anything meaningful. So the reason why we think this is more useful than some other approaches where they can only recognize some predefined activity is that we cannot foresee what the users may be interested in. For example, for me, shopping at a Costco is one activity, but if you're not a member of Costco, why do you care? So first, we logged all the mobile sensors. We logged the 3-axis accelerometer. This is for motion. Magnetometer for azimuth value for your heading direction. GPS coordinates for your outdoor location and trace. Rotation matrix, what's the orientation of the phone. Ambient light level from the light sensor, so that we know whether your phone is in your pocket or outside. Temperature sensor, we can estimate the environment temperature. Wi-Fi RSS, this can be used to derive your indoor locationing. Battery level, process list, which applications or service is running on the phone. This actually has a lot of security implications. Network stats, network traffic to and from the applications. At first, when I first gave this talk several months ago, I said this is trivial task, right? If you just have a graduate student and they can just look at the API and write a few lines of code. But people protested that in the audience, saying, no, this is not trivial. We spent years trying to get this working, because all the sensors, when you query them, there's no timestamp coming back. So you don't know whether, you query for GPS, the GPS receiver will return some coordinates to you, but it could be like several seconds later, whatever the process is running, or because of interruption because of the receiver. So you really don't know what time the GPS coordinate is associated with. It's the same thing for all the sensors. So last month, I went to the Qualcomm symposium on context-aware computing, and there was one guy from Georgia Tech who said, Qualcomm people, can you please add the timestamp to the sensor API? It just took us so much time just to get this part done. So it's not trivial. The other problem, just to give you an example, is that when your screen is off, a lot of function is shut off. For example, you cannot query your accelerometer readings when the screen is not on, which is not useful in the sensing stuff. So our smart students has to work around the OS to get this part done. And there was, the Nokia people was asking, what's your little secret? We can't get this working. I said, yeah, my students figured that out. So it took them quite some time to get all these little tricks working. Now, robustness. You don't want your sensing application crash every 5 seconds or every 5 minutes. What about transparency? You don't want your user to constantly be aware that there's something sensing on their phone, making their application slow, draining their battery too fast. So you want this sensing application to be as transparent as possible so that the users will be happy to use it. Power consumption, that's a big story. As I said, if you turn on all the sensors blindly, battery will be out in 4 hours. People will not use that. So a key problem in mobile sensing, and the main feature that separates us from all the competing platforms, is getting the user to annotate their activity. How do we motivate the user to give us annotations about what they're doing now? Because that will give us a lot of information so that we can do the study following that. The first thing we tried is to ask the user to annotate their activity, right? They just take out the phone and provide an annotation saying from 12:30 to 12:45, I was having lunch. From 12:45 to 12:50, I went to CMU building. But that's just not very useful. If I'm asking you now, can you tell me what time did you leave your office and come into this building? Any of you remember that, the exact time? Probably not, right? So that is probably not a very friendly UI for the user. And the first release with this approach, we got only 21 labels, 21 annotations in 2 weeks. And 71% of these labels were done where the event was happening, that user was actually annotating the event where they were doing something. But no one label happened more than 20 minutes ago. They cannot foresee what they will do in about 20 minutes. And no one label events were going to happen, and the users are less likely to label the same activity twice. So if I annotated that I'm walking on campus, I'm not going to annotate I'm walking on campus again, because I got the perception that the phone should be smart enough to figure that out, right? Why do I have to tell you twice? I mean, walking, it's just a walking. So this was not very successful. So the second approach we tried is to apply automatic activity segmentation first on the mobile phone. Now the key idea is that if we can represent all the sensor as a stream of symbols, then we can apply the sliding window, a pair of sliding window, and calculate the difference between these two windows based on whatever stream distance you are comfortable with. In this particular case, we used n-gram precision recall, basically measuring how different these two sliding windows are. And this will give us a value of the difference of the activities at that point, before and after. And that gives us the activity change curve. So we go through this window, and at each time we calculate how different the activities are before and after at a certain point. So you see the activity change as a curve here, and the peak is a good indicator that something is different, where you have been doing something different at that time t, before and after. And based on that, we can have a segmentation of the activity. And this activity segmentation turns out to be quite accurate, even though this is a very simple algorithm of just using a sliding window. And you can see for different activities, this is the segmentation accuracy, okay? This is not recognition accuracy. For example, driving, we got about F1 score about 0.8. So the driving activity, we can separate them from before and after with the F1 score about 0.8. For given presentation, attending class is very high, it's 0.1. F1 score is 1. The reason for that is, for those activities, their before and after activities are very different, quite distinguished from each other. Whereas, for example, the low F1 activities are, for example, eating. The reason why the F1 score, the precision recall for this is low, is that before eating and after eating, there's no very obvious boundaries before eating and after eating. You're just probably doing something very similar to each other. So yes.
Yeah, sure, but you're cataloging them into categories like attending classes because you know the higher level organization of the events. If you didn't know that already, all you would know is it's a low energy event, a high energy event. It'd be much more tricky to know what to do with those transitions.
This is actually just based on the low-level sensor readings.
Right.
This is only based on the motion at this time.
Right, but you know that why perhaps they were sleeping instead of attending class, sitting still, right? You know that they're supposed to be attending class, so you can say that makes sense to do it. If you just have that log, what you're getting is different levels of activity, but without a higher level framework, you don't know how to categorize those activities.
No, I think this is not trying to categorize the activity. This is trying to show the segmentation accuracy.
So you've categorized these for illustrative purposes, right?
Right, this is just for illustrative purposes to show for different types of activities how accurate the segmentation is doing.
And actually, you were very clear about that. In your description, you were just saying, in terms of segmentation, in terms of seeing these as differentiating moments with the sliding pattern. Anyway, I don't think you claimed that you were identifying them.
No, yeah, I said I'm not identifying the activity. We're just saying segmentation, right? Identify this is a different activity versus before and after. And the category here just to give you a better understanding why the algorithm works best for some activity but not for the other activities, because we are based on the before and after differences. And now for some activities, the before and the after differences are not so dramatic, then the segmentation may not be so accurate. We also applied a lightweight activity recognition. Now this is to assign a label to the identified activity. Now we want to do this on the mobile phone so that we are not applying a very heavyweight algorithms. We know there are many accurate heavyweight classifier, but because we want to run this in real time on the mobile device, we applied a very simple k-nearest neighbor classifier. So when user provided annotations of a few instances of some activity, for example, walking or attending classes or shopping at a Costco, we record them in a database and we record their feature space as the n-gram frequency. Okay. Now, with a new activities comes in, after the segmentation, we know that this is a new activity, then we compare this new activity A2 and calculate the cosine distance given their feature representation with all the existing annotated examples, and use the one that is the closest as the label, and assign that label to the new activity as the recognition.
So you're assuming it's a closed world, you know all activities.
Well, we have a threshold. If the similarity is lower, then it will be still unknown, and the user will choose to provide new annotations. So with that augmentation, with that functionality, now after this is second release, right? This first release where we ask the user to provide actual time and the label of their activity, we only got about 2.7 annotations per user per day. And with the second release, where we do the automatic segmentation first and ask the user to annotate activities that they are interested in, we got about 23 annotations per day. And the third release is that we allow user to share the activity with their friend. We got even higher annotations. And annotations is key in this research. If you don't get annotations from the user, you can't do a lot of meaningful stuff. Yes?
Have you thought about actually aggregating data across a lot of users?
Yes.
And saying, walking, I have a general model of walking.
Yes. Yes. So that's model sharing because this is still beta version and we're still polishing up our MobiSens platform. But once this is more finalized, we will release it to a much larger group of users and aggregating their model so that your walking will be shared with other users walking to bootstrap their models. So 3 months of having this app on marketplace, we are not very actively promoting this. We're just giving talks and tell people that we have this app running. This app has already been downloaded about 234 devices, roughly 234 users. We have been recorded 9,000 hours of data from 65 active users, and they have been providing 4,000 activities, 4,000 annotations. I probably contributed about 100 because I'm the most active user, but still 4,000 annotations is quite impressive. Power consumption optimization. From our experience, sampling accelerometer and Wi-Fi is not very expensive by means of power. The most expensive one is sampling the GPS. If you're sampling GPS at a flat rate, about 3 minutes per request, it can only last about 26 hours without any other functions turned on, right? If your phone does not have any phone function, no data connection, if you're just doing the sampling of GPS, the battery will only last about 26 hours. So we developed a dynamic GPS sampling algorithm based on idea that is similar from TCP/IP connection. You basically do not sample, or you double your sampling rate if there's no change of your location. So we adjust the sampling rate based on the location. We also use the Wi-Fi to tell us whether you are moving outside of the building or not. And this has increased the battery life about 25 to 40%. And empirically, from my own experience, if I don't charge this phone, and if I use my phone normally with the MobiSens turned on, this can last about 12 hours, which is already quite impressive. I think it's usable now, right? Because most of the people will need their phone for at least 10 hours before the next charge. On the MobiSens back end, we are doing more complicated processing with the mobile sensor data. Remember, on the mobile phone, because of the computing power, because of the power limitation, we cannot do a lot of fancy stuff. On the server side, we can do a hierarchical segmentation of the activity. So with all the sensor information load up to the server, it will generate automatically a hierarchical calendar entry so that you see what you do during the day. And this is the work we have just published at ICDM. It's called Helix. It's basically using natural language processing algorithms to induce the underlying grammar in human behavior. So this is inspired by work by Dan Klein. He's a faculty at Berkeley now. He did his PhD on inducing the grammar from natural language called constituent context grammar. And we're applying a similar algorithm on human behavior and trying to find out what is the underlying structure of human behavior without any supervision. Turns out to be quite interesting. So let me show you one day of my life. I'm not living in the Bay Area, so I'm actually living in the Central Valley area. And this is one day of my life where I took a discovery flight lesson around Tracy Airport for about half an hour. After that, I drove first to Livermore, and I bought a pizza at the Costco there. And I drove here to the Bay Area, met a colleague at Yahoo. Then I drove all the way to this campus. And as you can see here, this is automatically generated from my life log, right? It has different hierarchical entries. Some of the annotations are provided by me because I have never been flying before, so it doesn't know about this activity. So this is annotated by me. But driving here is created from the previous annotation. And the color shows the similarity between different activities, right? So you see driving to airport is very similar to driving to school because the sensor reading tells the system that this is very similar activity. Now this is showing as a hierarchical calendar entry. Now let me click on that, and this is actually the flying lesson part, right? This is the level where I get off my car, walk into the instructions building, giving me some ground lessons, and then I get on. This part is the flying, and flying is breaking down to several small activities. Again, this is done automatically. Now the first part of this small activity is called taxiing. That is, I hop on the plane, and the instructor was sitting next to me, explaining stuff to me, and our small airplane, Cessna, was taxiing from the parking place to the takeoff place right here. Automatically done, segmentation, okay? Then the second part is ascending. Surprisingly, I'm not expecting this. Let me see if I can. So this is the airplane. Sorry, too sensitive. Anyway, so the airplane took off from the runway and ascending, then turning, and here the instructor told me that we should descend. That is this part. Here. So this is airplane descending and then landed at the airport. And at this point, before I was landing at the airport, there was another small airplane ignored our radio announcement that jumped in front of us, caught in the lane. So we have to make an abrupt turn and waiting for him to land. So it was a good memory, right? If I don't have this, I couldn't remember what happened that day. It was quite scary because for me, I've never been flying before. And the instructor said, look, there's a small airplane there. It looks very tiny. It was just passed in front of us. And I didn't notice that. I was trying to land there. And the instructor said, make a turn, you will crash onto him. So, that's why I need a life logger. Then after that, I walked from the parking space back to my car. Then another level is I left the airport, drove all the way to office. And I first drove from the Tracy Airport to Costco Livermore, Costco at Livermore. This is the driving part. Then I get off my car at the Costco and went to the pizza place, bought the pizza, so on and so forth. I left the Costco, continue driving from Livermore back to Bay Area, and first arrived here. And without live log, I couldn't remember what happened that day. Then I looked at the live log. I realized that I actually had a meeting at Yahoo with a friend. This is at Yahoo headquarters. No, this is still Livermore. I think it's here. So driving here and driving to work. First stopped at Yahoo, meeting a colleague there. Let's see, where's the trouble? Yeah, this is Yahoo headquarters. And after that, I drove from Yahoo headquarters all the way to our campus here. So again, this is very useful to me because this is basically a live logger, and you can't imagine that I need to write down some logs where I'm flying an airplane. And with this, it really gives me a good memory of what happened that day. Now, that's what we're doing, and we're building a lot of interesting applications based on the mobile sensing. And the first application is called activity recognition through language modeling. If you're familiar with natural language processing, language modeling has played an important role here. The basic idea is that if you have a collection of data, you can train a language model that reflects the in-gram distribution of that data. So if you have a collection of politics, you have a collection of the sports data, you can train the language model from these two collections of data, and then you can use this language model to estimate an unseen sentence's likelihood to be generated by these two domains. For example, the sentence, President Obama has signed the bill of blah, 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 is more likely to be created by the politics domain versus the sports domain. So if we do the same thing with the behavior, we can train the language model from different activities. For example, if I train the language model of walking, of running, or cycling, then for a new sentence come in, I can estimate how likely this new sentence, sensor sentence, is created by the certain activity, and turns out to be very high accuracy as activity recognition. So second application is called anomaly detection. This is also inspired by natural language processing. For example, we know Shakespeare has been writing a lot of plays in the past. Now, somebody from England just came out saying his great-great-great-great-grandmother has just left him a play and it's written by Shakespeare and is asking you for $1 million to buy it. Will you trust him? Then what people do is that you can train a language model from all the plays by Shakespeare in the past. Then you can estimate the probability of this unknown play to be generated by the Shakespeare's language model. Now, if the probability is lower than a threshold, it's like, damn, you liar. If it's higher than a threshold, yeah, you just found a lost play by Shakespeare, and you can give this guy some money, and sell them whatever. So that's the idea. Now, as I said, my phone is recording everything about my life. Have a book of joy. If we have all the data, we can train a model of my normal behavior as what joy should do, or what I usually do. I usually drive from home to here. I usually go to the Costco to buy pizza, but I will never go to some strange place like cycling to Mount Hamilton. I know Ted would usually do. So if we have that model, and now if we have a new sentence come in from your sensor, you can estimate how likely this new sensor data is created by user's behavior model. Now, if the probability is lower, then something is wrong. So in the case, for example, elderly users accidental fall, or Alzheimer's disease seniors wandering around the street, which is actually a serious problem. They just don't remember what they're doing. They walked out of the street and they couldn't remember the way back. Now, with all this abnormal behavior, then your mobile phone can flag some signal to tell the caregiver or tell whatever security measurement on the phone to take some actions. Here's one paper we published at ICCCN is using the Wi-Fi RSS to derive the indoor locationing. So if you have your Wi-Fi indoor locationing stored on your phone, you can build a trace model, right, where you usually show up in the building. Build about 8 hours of your data, we can derive a very reliable model about your behavior inside the building, and now we create a simulated event that your phone was snapped away by your colleague. So this is the normal trace of the user from pink to red walking around this way. And now we splice the data from another user to simulate that the phone was taken away by the blue user. And we can show, as shown in this graph, that we can reliably identify that the phone was stolen, was taken away, so that we can protect the data sabotage from the mobile devices. A similar idea was tested with the GeoTrace outdoor, so that we know when the user, when the mobile phone is traveling off the regular track of the user. The third application I want to show you is called SenseCare. This is published this year at the MobiCase. A very similar idea. If the senior choose to age in place, then the senior can carry a mobile phone, and this detects all the activity, the normal activity of the user, and the caregiver or the family member remotely can look into the life logger service so that they know what the senior is doing, so that they can better understand their life, giving them suggestions whether they should spend more time in the community or outdoor, or in case of abnormal activities such as accidental fall, the caregiver or the family member can intervene in time. Right? I heard a lot of cases that the senior fell down on the bathroom floor and nobody knew that, and after a few days, miserably they passed away. So this is actually using the smartphone technology to help that event. To conclude my talk, the core idea in our effort is to use behavior text representation as an effective method to represent or model human behavior. Despite all the challenges, there are great opportunities and exciting applications that can be derived from mobile sensing. We have been developing a CMU MobiSens, a social sensing platform, and we are very excited to see what this can turn out. Some of the ongoing work by expanding the work to society level for society sensing and behavior, and develop behavior-aware mobile applications. With that, we published a lot of papers, and with that, I can take some questions. Yes.
It seems obvious if you, instead of labeling by user, think of Google or whatever, you're constantly trying to sell things, right? That's the world that pays for the phone. So context-specific services,
yes,
you have false positives, false negatives. It's called click rate. So that's where the money is, right?
Yes.
So couldn't you trick the user in some sort of a positive reward system, labeling by looking? You know, you walk into Costco, you're looking for a better deal than the stuff you're looking at.
Right.
So very interesting to find out it's even cheaper next door, right?
Mm-hmm.
So if you act on that, then you were in Costco, or you were actually shopping, not in the bathroom. So.
Or based on your past behavior that you are looking for,
so
whatever. Yeah.
It seems like the phone is only so smart. The user's always going to be smarter.
Yes.
You got to get the user to do something.
I think that would be the next step. It's a very interesting idea. Yes.
I guess the follow-up to that is just how do you feel about the requirement of people to interact with the phone at all? How, in your experience, has that been? How has that worked out? You said a little bit about that earlier. It's very interesting.
Right. Topic. So I think incentive is critical here. How do you motivate a user to interact with your system to provide annotations? From my experience as a developer and also as a user of the system, if the system gives me a reliable, quite accurate activity segmentation, and some level of activity recognition that motivates me to provide more annotation. If the segmentation and the recognition is not accurate, it just makes me feel the system is dumb and I don't want to provide additional annotation to that. Also, the incentive that I can see my activity on the live logger server is a good motivation for me to provide more annotation, more correction, and use the system more, because I find that is valuable or is useful to my life, that I can find out what happened to me.
I always like to get some students to ask questions. Is there any student that can ask a question here?
Some of students are the developer of the system.
Yeah. They might even got a better question.
Yeah.
What do you guys want to ask a question? Maybe Nisha? You have a question?
I was thinking about the reliability of the segmentation. What you're doing.
Go ahead.
How do you identify the activities preceding and following an activity? I mean, as your graph suggested, that some activities are very hard to identify.
So we're not identifying the pre and the after activities. We're just finding out how what is the change of activities at a certain time.
Right. So, for example, if you're sitting at a table and working,
Mm-hmm.
and if you're sitting at a table having lunch,
Yes.
how would you?
That depends on your sensor. So if you're only having the motion sensor, then you cannot distinguish these two activities. Right.
But you never distinguished the semantics in either activity. You only distinguished first I was doing activity 1, and now I'm doing activity 2.
Yes.
That's all.
Yes,
Okay.
for the segmentation.
Right.
Then the annotation will provide the, yes.
So it's essentially a value function if I want to simplify my mind.
Yes.
And as a discontinuity, and that's the grounds for the segmentation.
Exactly, exactly. So you don't have to type in the time saying that from, yeah. But this makes a huge difference from the experience. Yes.
Yeah, I'm wondering how, to me, this seems very closely related to kind of social network type of application. Do you see it almost merging into some kind of social network kind of thing instead of being a, you need the life logger application, and then you need some kind of maybe social network application for sharing purposes. Do you see them as separate, or do you want to, do you see them as almost merging into one?
I see they are complementary to each other, right? You can rely on the online social network to add people to your friends network so that you can share the activity to them. On the other hand, the mobile sensing brings in the different aspect of the physical world. I usually use the example that I don't even know my neighbor's email or their Facebook ID, but of course I have some social connection with them. So when their kids bring out to the trick or treat, I bring out my kids to trick or treat. So we have some social interaction to each other. But we actually have no online activity that is measured by the current social networks. So in a way, they're complementary to each other.
Anybody that hasn't asked a question, maybe have a question? Maybe the last one.
But there's another kind of interaction, like if you look at apps on the iPad like Waze, they share a common model because by definition they're doing a common thing, and everybody is a traffic sensor.
Right.
And they share the semantics of participating in traffic.
Yes.
And that's different than synthesizing an activity and then sharing the model, because it starts with a shared model. And it's not clear I get to the same place by inducing something I want to share, by knowing I'm starting out interested in sharing.
You're not sharing your model, you're sharing your activity.
Well, in the case of Waze, you're sharing traffic, you're sharing driving, you are sharing the higher level activity. At the outset, can you agree to join in the activity to run the program?
So the sharing part was actually motivated for another application. The DARPA is looking for the ground reporting system, where the soldiers nowadays, at least that's the idea of the military, to give the soldiers a smartphone. So they needed the soldiers to report constantly what they're doing there, for the commander to understand where his troops are, what they're doing, and also for knowledge transition. So when one unit was dispatched to another place, the unit taking over the responsibility of that area has to know which route actually has more IEDs, has more insurgents. Now, in the current situation, they have to pass in the notes, which is not accurate at all. So for that, you have to share your activity for horizontal information sharing, so that I know a brigade or platoon company C is engaged with the insurgents crossfire in that area. So in that sense, that's what we meant activity sharing.
Another example of this where you could probably get money without too much effort is if you did some kind of disease reporting for vectoring purposes, who has SARS where, for example.
Right.
And then you denoted it on a geographic area to know trends. You could probably make a
Yes.
for it.
There was Google actually did something by just following the query of flu and actually show how the flu actually spread around the country.
Well, because people have meetings at 2:30 a lot of, and this room gets reused. I'd really like to move this discussion out into the hallway. We have cookies and soda for everyone. Thank you, everybody, for coming, and thank you very much, Joy, for the great talk.
And if you want, you can download the MobiSens. That would be a good support for our research. All right, thank you. And let us know about your feedback.
Supposing I'm observing outside.
Oh, sure.